Hey class, if you remember from last time, we had this open-ended question of whether or not, or given that it is possible, how to run through a collection of numbers, an array of numbers, and test whether or not any two of those numbers, any distinct pair of numbers from that set, adds up to some given test value. So let's return to the code and I'll show you the answer to this question. Okay, so we have our array, our test value, and our declared variable name has some, but we haven't assigned it any value yet. So let's go through and create the function for it. So we have our test array and our test value. And so the question of whether or not to end a semicolon in JavaScript, I typically do. Sometimes I leave it off whenever I'm writing against the interpreter directly. But whenever I am writing a JavaScript file, when I'm editing a JavaScript file, I always leave it on. Okay, so I said it can be done in a single pass. So you're going to need a local variable, and it's going to be a hash map. So that is the data structure that we need in order to gain constant access. So let's see. We'll call it our looking for map. And you'll see why we call it that in a second. So this is the syntax to create a new JavaScript object. Okay. And so JavaScript objects, Json, is in other languages it's known as a dictionary or a key value map or a hash map. So you can set as the key any JavaScript value and then there will be a value associated to it, or definitely any literal value. I need to backtrack. I don't know, even if they allow you to use an object as a key, I don't know whether or not that necessarily makes sense. So you would typically restrict it to just numerical values or strings as your keys, but it may be possible to use other values as your keys. Anyway, so we again have our outer loop. Which will iterate over the length of the array. If we don't find our value, we need to return false. And then within the array, we need to see if looking for the current value here, and I'll set it as a constant. And so this variable comes off it's scoped to the loop, and so it'll come off every time the loop recreates itself, every time it iterates through, and it'll create a new current value. If I wanted, I could declare it as a let. Perhaps that makes more intuitive sense, but it's constant for each pass of the loop, which is why I declared it that way. So let's see if we haven't caused any harm by doing that. So this is our current value, and so if our map contains the current value, if our map at the current index has a value that is exactly equal to current value, so not undefined and not something else. In other languages, the syntax for this would be a little more complicated, but JavaScript is very kind about this particular case. So I'll use curly braces here instead of doing it in one line, just for familiarity of style. So if it has that value, then return true, because we have our sum. Right? Otherwise, then we need to leave a hint for any future tests that are looking for exactly this. So then otherwise, what we need to assign I was mistaken, that should be current value. And we don't need to test whether or not it's equal to it, right? Because we're looking at the key. So then we're going to assign the complement, and we're going to key it with our matching pair. So const matching, we'll call it complementary value, is equal to test value minus current value. And so the value that we'll associate at the key, the complementary value, the one that we'll test for whenever we get to some future place in the array, is just true. So that if the value at that key, at that complementary value, is true, so if true, then we have a sum, because this is equivalent to saying we have the logical equivalence that test value is equal to complementary value plus current value. Right? If we just add current value to both sides, it disappears over here and we get a positive over here. Right? So we're using that same property. So you just have to be a little bit clever, and then you can make that assignment. So let's run our test. Oh. Yeah, always introduce some flaw, otherwise the universe will lose it. Okay, so we'll test that again. So as expected, 26 was not in there, and then we know that 3 is in there. So it appears to work. We did it in just a single pass, and as promised, in order to get that quicker performance, the better runtime, we needed to invoke something that would increase our memory footprint. So all is as expected. It is possible, and now you see at least one potential use, like one clever use for one of the data structures that we've already discussed. But in actuality, the key value mappings, the hash map, the dictionaries, whatever you want to call it, are just extremely useful in general, right? So this is kind of some exotic usage for it, but as you become more and more familiar with programming, you'll see exactly how desirable it is to have some key value maps. So. Okay, I believe yesterday, whenever we left off, we left off right here with the example for the principle of inclusion and exclusion. So you can read through the notes to get the explicit explanation of exactly what's going on here, but this is the question that this answer expounds upon. So if you're given 1 byte, so a bit string of length 8, and you want to know, you want to count, like for future instances where you're trying to count the number of events or the number of outcomes that satisfy a particular event, then you need to know how to count correctly so that your probabilities add up to 100%. And hopefully, if I move quickly enough, we'll get to that in this class. So we want to know how many bytes out of the 256 possible unique representations of the 8 bits either start with a 1 or end with 2 zeros. And what we're going to see is that these possibilities are not necessarily mutually exclusive. So it is possible to have the number that starts with a 1 and has 7 zeros right after it, and that would satisfy both conditions. So whereas before, where we were talking about the subtraction rule, it's not just adding up all of the numbers that start with a 1 and all of the numbers that end with 2 zeros to get the answer to this. We have to correct for the number of outcomes that were in both sets. So we have to subtract the intersection of these two. Right? And so here we see that there are 128 out of the 256 that start with a 1, and I use degrees of freedom as a term here, and all I mean by that is that it can be either a 0 or a 1, and it satisfies that whatever condition that you're talking about. So so if you just count based on that, then you can see the number for that first condition. And then set B, the one that ends in 2 zeros, has 6 degrees of freedom. So the 6 most significant bits can all be 0 or 1, so long as those last 2 bits are 0 and it's still satisfied. So there's 2 to the 6 or 64 of the possible 256 binary representations of an 8-bit string that satisfy that second condition. So the intersection, A intersect B, happens when the most significant bit is 1 and the least significant bits are 0. So we're locking those in place, and the other 5 bits, the 2 to the 6, 2 to the 5, 2 to the 4, 2 to the 3, and 2 to the 2, those bits are all free to be either 0 or 1. And so that means that there are 2 to the 5 or 32 outcomes in the intersection that which satisfy both of our conditions. It starts with a 1 and ends in 2 zeros. So there's 32. Okay, so using our subtraction rule, it's the size of set A plus the size of set B minus the intersection of the two. So we add them together, we get 192 minus 32, and that's 160. Right, so that's the application of the subtraction rule. Okay, so the pigeonhole principle. It is a really simple concept. Right? So formally, if k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more of the objects. Okay, so if you think of okay, so let's say that you're given a stack of flyers, a stack of we'll say 200 flyers that you have to pass out, and you having access to the school's mailroom, or let's say you're given 200 flyers. So you have these 200 flyers, and there are 199 mailboxes for you to stuff these flyers in. So you put one in each of the mailboxes because you're not supposed to give anyone 2. Then what the pigeonhole principle says is that if you want to get rid of all of your flyers, then you're going to have to stuff at least one of those mailboxes with with 2 of them, right, in order to satisfy your quota, in order to be done with your work of passing out those flyers for the day. And so it doesn't seem all that profound. It seems a little bit obvious, but it is kind of important in that it means if you create a structure like the hash map that we used earlier, and you request some amount of space in order to house your hash table, your hash map, then it essentially says that, well, you can't, you're going to have a collision after on your k plus 1th object that you stuff into this hash map. You are guaranteed to have a collision. You're guaranteed to have a second item stuffed into one of these slots, and so it tells you, in the best case scenario, how long, or how many items, the capacity of your dictionary or your hash map or whatever you want to call it, before you start running into a collision. It also means that, like if you think of encryption, which we're representing as these arrays of bytes, then you can only uniquely encrypt so much data into a given space, right? So there's only so many unique representations, and beyond that, you either need to expand the amount of data that it's taking up, or so forth. But I think a better example than encryption would be compression. So you can define whatever rules you want for compression, but eventually you can only uniquely, like if we're using deterministic algorithms, which we must if we want to be able to decompress our data, then there are these rigid rules in how we interpret this compressed data and how we can extract the data from it. And so you can only go so far and still uniquely represent some data that can be extracted. And so the Pigeonhole Principle just says that there's these limitations in how much we can compress something, or in terms of like hash tables and how much data we can stuff in there before we start needing some alternative resolution for stuffing these envelopes and these mailboxes, or these pigeons and these pigeonholes. And so it's a really simple concept, but it is important, right? And so just like everything else, from these simple ideas, we will build up more interesting results. Okay, so a function f with a set of k plus 1 or more elements to a set that maps k plus 1 elements or more to a set with k elements is not one-to-one. And so if we discuss compression, right, so you're mapping well, that's not a good example, but yeah, basically if you're bumping something, you cannot uniquely represent every one of these items if you're mapping to a smaller output space. So for continuous functions, it's a little bit different. So if you think about the function 1 over x, so you can map every value that's larger than 1 to some value that's between 0 and 1, just by inverting it, by changing it from from x to 1 over x, right? So anything larger than 1 will give you a ratio 1 over x that is smaller than 1 and greater than 0, in fact. And this correspondence is 1-to-1, and so the interesting result is that in this continuous case, there, by this example, there are as many numbers larger than 1, in as many real numbers larger than 1 as there are real numbers smaller, or between 0 and 1. And so that sounds basically impossible, right? Because if you take a number between 0 and 1 and you add 1 to it, then you get a unique number between 1 and 2. And if you add 1 to that, then you get a unique number between 2 and 3. But you're dealing with the same set, right? These numbers between 0 and 1. And so it would seem that we just have these copies of it. So how is it that we can have 2 copies of it to the right and just 1 copy between 0 and 1, and just by flipping it from x to 1 over x, we've somehow mapped 1 to 1, right? And so infinity does create these interesting seemingly paradoxes, and so you have to create these really fine seams for how we discuss these things. But that's all pretty nasty, and so they wait until you're either a senior undergraduate or a graduate student to really discuss these things further. So it's interesting to think about. But whenever you're dealing with integers and whole numbers, then and in particular finite sets, so just some number k or some number x, whatever that is strictly less than infinity, right? Then you can make you can make more rigid statements in these discussions, and so basically all this says is that if you go to a school dance, right, and you have you line up the students along the 2 walls, and one wall has k plus 1 students and the other wall has k students, and you ask them to pair up with a dance partner from the other wall, and they must come from that other wall, then you're not going to be able to fully do that. Either one dance couple becomes a dance triple, or they fly solo. They're unmapped, right? They have this undefined value, and so that's what this corollary is saying. Okay. Okay, so I go off a bit on this tangent about compression, and so I think it is interesting, and take a moment to read the notes, and you can ask me about it later if you want. But since I'm not really testing over chapter 6, I'll just leave this to you, whether or not you find the discussion about how the principles of compression algorithms and how we can achieve that. Anyway. Okay, and then this says, so the generalized pigeonhole principle deals with this fraction, right? And so it says that if you have k boxes, right, and in objects, so it's always easier, I feel like, if you use concrete examples. So if you have 12 basketballs, and you have 4 trash cans that you're stuffing the basketballs into, and you have to get them all put up, and these are your only options, these 4 trash cans, then you can't say that they all have the same number, but what you can say is that at least one of the trash cans will have at least 12 divided by 4, so at least one of the trash cans will have at least 3 basketballs in it. And if you were to increase that number to 13, you would see the ceiling operator here. And so we would say that at least one of the trash cans would have 4 basketballs in it. And so again, you can't guarantee that they're as evenly distributed as possible, but what you can say is that we know at least a little bit about it. At least one of the trash cans is pretty stuffed with basketballs. Okay, so permutations and combinations and R permutations and yada yada yada. So this is the continuation of the product rule. So in the last lecture we discussed office assignments and choice of the office. And if you have 12 offices and 2 employees and you let them choose, then the specific arrangement or assignment of offices for the first person, there are 12 possible outcomes. And then if we combine that with the second choice, there would be 11 remaining offices for the next person. And so if we continue that on so that we have 12 employees and they each get to pick an office, then there are 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 possible assignments of those 12 offices to those 12 individuals. And quick tangent, if we had a 13th individual, then we would know that at least one of those offices was carrying 2 people in it, right? So, pigeonhole, right? Okay, but the example we used last time, the ordered arrangement or the particular assignments, was an example of an R permutation. And so the R permutation is just another name for the product rule, where we're allowing them to select but without replacement. So we've discussed factorial, and here's a definition of the R permutation formula, and it's exactly what we showed earlier, where it's of this form, right? N factorial divided n minus R factorial, or the product formula, which is what we were seeing before, where we're choosing our, we're making our selections from some set, and we care who goes in what office, or who drew which card or whatever, right? So that's where this formula comes from. It's just another version of what we saw last time, but now it has a new name. So in addition to being the product rule applied to some scenario, it's now called an R permutation. Okay, and then the ambivalent version of the permutations are combinations, or the ambivalent version of our R permutations is combinations. So we discussed this earlier, how we would derive this, and so it's an R combination, so something where we've selected R items out of a set of n, but we don't care about the particular assignment. We just want to know how many different sorry. Yeah, sorry. We just wanted to know how many different combinations there were in choosing these R elements from there, right? So we didn't care about order, but yeah. Okay. Here, let's backtrack to the last lesson. Okay, so yeah, here we had chosen K offices, and we got our product notation. to see how many different ways those three individuals could have selected those three offices. But if we didn't care who got which office, if we only wanted to know the likelihood that any given three offices, so the three offices nearest the door or whatever, what are the chances that they had selected those three offices, then we would use this formula. We would divide out the order in which they drew their lots. We really don't care about that. We just want to know what are the chances that they took up those three closest to the door. Okay? And so that's what this combination formula is for. Okay, so now that we've counted our way to formulas and permutations, R permutations, and combinations, or here they call it R combinations, but I've always just seen it as the formula for combinations in choose R notation. We can move forward to discrete probability. And so this is mathematics for gamblers at last. Okay, so first we'll start with just some basic terms. So an experiment is just another name for a trial, or an instance, or an event, or it has many similar names, but it's not exactly a science experiment. It's just testing possible outcomes, testing the likelihood of events. And so if you don't really know what's going on, or what the likelihood of anything is, then you just have to sample, right? And so I think a great example of this is I believe it was Mendel or Mendelssohn. I can't exactly remember, but the monk who is known as the father of was it the father of genetics, or the father of genetic traits, or whatever, and so he, if I recall the story correctly, he was gardening, and he noticed that some of the pea plants were taller than the others, and he wondered what it was about these peas that made some taller than others. And he took what he knew about the way that people tend to look like their parents, or draw traits from their parents, and he made the hypothesis that plants were getting their phenotypes, that plants were getting these traits from whatever plants that they were breeding with. And so he performed these trials, he performed these experiments where he bred them together, and he tried creating these different genetic lines, and he kept them separate, and he kept rigorous notes, and he had time to burn, so he was kind of able to do this. And so he took a sample, and he took a sample space, and then he measured based on the outcomes how, just from taking a large enough sample size, how likely it was that a given trait would show up, right? And then we can continue this example or this discussion as we go forward and say, okay, well, given that both parent pea plants were tall, what is the likelihood that the child was tall? And then if all four grandparent pea plants were tall, what is the likelihood that the child was tall? And so forth. And then he was able to take these counted events and go back and extract these rules that, well, it must be passed down, and the probability of getting the dominant or recessive trait would be 50-50 or whatever, right? And so he very much used techniques that the sorts of techniques, though perhaps without the formalism that we'll be using here. But as you read these terms, and as it seems really foreign, just keep in mind that they come from discussions of a similar nature, where you're not using these well-known functions. You're just asking the question over and over and over again, and you're creating this sample space, and then you're going back and analyzing the data, and whatever it is that you're testing for, whatever event you're looking for or outcome you're looking for, you count the number of times that happened in the overall sample space, and that is your probability of that event. And then you kind of go back and you derive the probability function. And so in some cases where it's well known, and we'll discuss like the rolling of die, or a roulette wheel, or anything like that, where it's very it's got this uniform distribution, everything is equally likely to happen. So in those cases, the probability function is very intuitive. Like we know what we're doing. In other cases, and in cases where terms like this come from, and like this, you don't know, and you go back and later you fill in that probability function later after having made these test results. So, but we'll keep it simple going forward in these examples. But I just want to lend motivation to where these terms come from, right? Okay, so the example that we give here, or following on that, the probability of an event is the number of times that the event occurs, so tall pea plants, over the entire sample space. And then over here we ask the question of, what are the chances that you roll 2 dice and you get a 3? You roll a 3. Well, there are 2 ways to get that. So if you have a white die and a red die, or if you just labeled them A and B, then the first way is if you get a 1 on the white die and a 2 on the red die, or alternatively, if you get a 2 on the red die and a 1 on the white die, or sorry, you get a 2 on the white die and a 1 on the red die, then either of those would satisfy the criteria, the outcome. And so in that case, there's 2 possibilities that satisfy the event you're testing for, and there are 36 from the product rule. There are 36 possible outcomes if you care about ordering, right? So the number of outcomes from A times the number of outcomes from B. So given that ordering, then there are 36 possible outcomes, as opposed to the 11, right? So you can roll anywhere from a 2 to a 12, but each one of those possible events has different probability, and so your sample space is derived from this, if you have that ordered set, right? So then the probability of rolling a 3 is 1 out of 18. So 1 out of every 18 times you roll 2 dice, you would get a 3. Okay. So now we have another theorem, and it's the probability of the complement, right? So what are the chances that I roll anything other than a 3, right? So not a given event. Instead of asking, directly, what if I ask for not this thing to happen? Well, it's 1 minus the probability of whatever it is that you don't want to happen, right? So the chances of not rolling a 3 is 1 minus the probability of rolling a 3, or 100% minus the I don't know, it's got to be like a 0.5 or 0.0, sorry, a 5.2% chance or something like that of happening. So then you have like something like a 94% chance of not rolling a 3. which is pretty good. Okay. And then this is the application of the subtraction rule, which is kind of why I wanted to stop there the last time. Let's come back to see it. So, okay, so if we have two events that we're measuring, so the well, I'm having trouble thinking of a way to do this with the dice for a minute. Give me just a second. Okay, so let's say that the first event is that. Okay, so again, if we label our dice A and B, and we have event 1 is that die A is a 6, and event 2 is that we roll an 11, right? So we just care about rolling an 11. Well, these aren't, there is some overlap in that. So we have that this outcome, or the probability of getting that OR operation, right, is equal to the probability of rolling a 6 on our white dice, or white die rather, of plus the probability of rolling an 11 overall, minus the 1 out of 18 chance that we have rolled minus the 1 in 36 chance that we roll an 11 where the white die is 6. Right? So that'll happen 1 out of 36 times. 11 and that first die, the one that we cared about, was 6. So we would have overcounted by that if we just did simple addition. So this is just the subtraction rule. So we've kind of already derived something very similar, or arrived at a similar conclusion. And so this is just another form of that rule that we're already familiar with. So we've overcounted something, but we can add them together separately and then correct for it. Right? Okay. So now, probability theory in general, and it just basically says that, okay, so now if you have a sample space, whether it's the physical characteristics of pea plants or the roll of dice, then the probability of the outcomes is never less than 0% and never greater than 100%. Right? Regardless of what you're testing for, it can do no worse than 0% or no better than 100%. And whenever you add up all of those probabilities, it needs to add up to 1, or it needs to add up to 100% of all of the possibilities. So it's we're not requiring a lot, but we are formalizing what we require. And it basically says that you're bound between 0 and 100%. And if you add up everything that could happen, then that's 100% of the things that could happen. So again, we're not saying a lot, but we're formalizing it. Okay. So probability distribution it's a function, and it indicates just the likelihood of any particular event. So for the roll of the two dice, we have that P would give you the probability of getting a 2, a 3, a 4, and so forth up to a 12. And those values are not going to be identical. They'll be symmetric, but they won't be identical. So they're symmetric about the value 7, I believe. Okay. Yeah, so that rolling a 2 is just as likely as rolling a 12, rolling a 3 is just as likely as rolling an 11, and and so forth. And then the most likely event is that you would roll a 7. And then using this, we can see that, well, we can actually define the likelihood of rolling numbers other than something, an integer between and including 2 through 12. The probability of rolling a 0 is 0. Right? The probability of rolling a -1 is 0. And so it's defined for other numbers. Our distribution is defined for other numbers, but it's going to be 0 outside of the actual domain of possibilities. So we can limit the values that we test for just by applying a minimal amount of intelligence to it. Okay. The discrete probability function is what I just told you about the roll of the dice, where we're dealing with integers, and in this case, we're going to be dealing with finite sets of integers, so that these are the possible values, and it maps it to some probability between 0 and 1, or if you want to think of it as a percentage, some percentage of likelihood between 0% and 100%. Okay. And then, as before, if we add up this finite set of possibilities that we're dealing with, then those values, those probabilities add up to 1. And if this isn't the case, then either you've excluded something that is possible, or you haven't properly corrected your probable outcomes, right? So maybe you have some scenario like this and you haven't corrected for some value that was counted twice or whatever. But this is very much a reasonable condition, so that if you have independent events that you're measuring, then the probability of these events should add up to 1. Right? Otherwise, you've messed up somewhere else. Okay, but I mean these are just formal definitions typically. So okay, and then here's an example again using dice where we've labeled our die A and B, and we're explicitly counting the scenarios that satisfy the condition we're looking for. So if we're looking for a 2, then both A and B must be 1. If we're looking for a 3, then it can be A equals 1 and B equals 2, or A equals 2 and B equals 1. If we're looking for a 4, then we can have 1 and 3, 2 and 2, or 3 and 1, and so forth. And then if we went through and we did this for all of the events between 2 and 12, so every possible outcome, and then we added up the fractions, then those fractions should add up to 1. Otherwise, we've messed up somewhere, right? And so that's what this condition is saying. So if you get there and it doesn't add up to 1, then you've miscounted or you've done something wrong. Okay, so it's a test for success. So uniform distribution is what I was talking about with the roulette wheel as opposed to the roll of the die. So uniform distribution, if you have n possible outcomes in your sample space, then every one of those events is equally likely, and so you have a 1 over n probability. So that if you make this sum, then you have n times 1 over n equals 1. That makes sense, right? But the key of uniform distribution isn't some formalism like this. It's that every possibility is equally likely. And so the roulette wheel is an example of uniform distribution. Okay. And then, let's see. Okay, so the probability of an event as described above, right? So the probability of rolling a 4 is the sum of the samples that will satisfy it, right? So it's the sum of 1 and 3 plus the 2 and 2 plus 3 and 1. And so that gives us the probability of our event, right? So it's just the formalism of something that we've already seen. And so it I understand how it can get confusing, working through the book, and it all looks really familiar. And some of it, to be fair, is repetitive. But for these definitions, really, we're just we're developing a vocabulary so we can discuss these problems. So just bear through it. Right? Okay, and so this is a theorem, and again, we're still dealing kind of with fundamentals. So don't expect it to be kind of simple as we start. And so this one says that if you have a sequence of pairwise disjoint events in a sample space S, then the probability of the union of those events is the sum of the individual probabilities. Okay, so what does that garbage mean, right? We've said a lot. What exactly did we just say? And so essentially, this is an example of a union, right? So we had those, and if there's no overlap, right? So if they are disjoint events, so if you're asking for the probability that a team either won or lost a game, well, those are disjoint events, right? It's not the entire sample space if you're talking about soccer, where it's possible to tie, right? So then the probability of winning or losing, the union of winning and losing, right, is equal to the probability that you won plus the probability of teams losing. And so it's going to be, because ties exist, it's going to be some value less than 1. But in particular, you can think of it as subtracting the percentage of games where teams both won and lost. And so we're not talking about Pyrrhic victories or you won the game but you lost a player or whatever, but on the stat sheet where your team both got a win and a loss in your record, that's 0, and the probability of that is 0, right? And so this, you can either think of it as not being there or as correcting by 0 or subtracting by 0 or whatever, whatever's most convenient. But whenever you're dealing with disjoint events, like winning or losing, then the probability of the union is equal to the sum of the individual probabilities, right? So this, which is potentially a very intimidating formula, that's all that it's saying. And so that's basically all that there is to it. So however many events you look at, then it breaks down pretty simply. So if you think about horse racing, right, where I shouldn't have picked that example. I want to say that there's 8 horses racing at a time, but I can't exactly remember. So if you want to say the probability that either the first horse won, the second horse won, the third horse won, or the fourth horse won, it's going to be the sum of the likelihood that those horses won, right? And so if you're looking at, so you would think that it might be a uniform distribution or something similar, but there are preferred lane assignments for these horses, and those lane assignments go to the horses that do better in the trial runs or whatever, and so the best horses are going to get the preferred lanes. And so in addition to getting what is considered this biased lane, it's also biased in favor of the best horses. So the 2 horses don't win at the same time, right? They will go to the photo finish and get it down to the molecule that crossed the finish line first. And so only one wins at a time, so the events are disjoint. And it's not uniform, so it's not exactly trivial, but you're adding up the percentage of the time that the horses from those lanes won, right? So that's all that we're doing here. Is if you start saying, well, what if this or this or this happened? Well, that's a union of events, and you're looking for that probability. And in the case that they are disjoint events, that there is some mutual exclusion to what happens, then it's going to be the sum. And when that's not the case, whenever there is overlap, well, then you have to correct using our subtraction rule. Right? Okay. Okay. So now, again, continuing our vocabulary. So we have something that's known as conditional probability. Right? So the conditional probability of E given F, right? So E restricted to the case where F is true, E given F. The probability of E given F is the intersection of E and F divided by the probability of F alone. Right? And so before when we were discussing Mendel or Mendelssohn, right? I can't remember for the life of me right now, and his pea plants, then where this might apply is that if the probability that our pea plant, is tall, right? So some grandchild is tall, given that 3 of the 4 grandparents were tall. So this conditional probability is going to be this intersection. So the number of all of these times where that was the case, divided by the probability that 3 out of the 4 grandparents were tall to begin with. Right? And so there is a formula for questions of this form, right? So given that some condition, what are the chances that something happened? Right? And so this is the formula that you would use if you find yourself speaking in those terms. So independent events or like coin flips, basically. And so if you say, okay, so what are the chances that I'll flip a coin and I'll get heads, and then on the second flip I'll get tails, then it's going to be the probability of, so it's going to be 50% of the time, or 0.5 or 1/2 times 1/2, and so the probability works out to a quarter. And so you'll say, well, these are independent events. Isn't this always going to be the formula that I use? Well, no. So the probability that if you draw from a deck of cards is the ace of spades. If it's a full deck, it's going to be 1 out of 52. But if you have 5 people drawing, right, and or to make it easier on myself, if you have 13 people drawing, and you ask, what are the chances that someone drew the ace of spades? Well, it's going to be 1 out of 4 chance that the ace of spades was drawn. And so, but the chances, the likelihood for each person drawing the ace of spades is not equal, and so it goes up essentially with each successive draw. Anyway, but yeah, but this formula would not exactly apply, because the chances of another individual drawing it are very much dependent on whether or not it was already drawn, right? So if the ace of spades has already been drawn, then the probability, I guess they would have to be, distinct events or whatever. So perhaps that's not a perfect example. Sorry, I'm trying to come up with a good scenario for that. But anyway, coin flips are considered to be independent events. The likelihood of having a car accident at a particular intersection on successive days are considered to be independent, but the likelihood of having a car accident in successive hours would not be, right? So individuals are more likely to speed through an intersection if there aren't police and medical care people cleaning up the accident. And so if an event happened at 5 o'clock and you want to know the likelihood of it happening at 6 o'clock, well, it's dependent on whether or not there was an accident at 5 o'clock, and so this formula wouldn't apply. But in the day after day scenario, on successive days, those would be considered independent. Right? So there are scenarios that you can come up with where this doesn't come. But coin flips would be considered to be independent, and the roulette wheel, again, would be considered to be independent, and so forth. Okay. And then the ace of spades example, actually, I've been thinking about it. And so the likelihood that one of the individuals draws the ace of spades, and this is, it's blowing my mind. It's going to be, so you would expect it to be like a 3 out of 4 chance that they didn't draw it necessarily. But there's a 51 out of 52 chance that it's not drawn on the first time, and a 50 out of 51 chance that it's not drawn on the second time, and so forth. And so the chance that it is drawn by one of the 4 individuals would be the complement of the chance that it is not drawn 13 times in a row. And so I'll leave it to you to compute whether or not that is exactly equivalent, right? But I don't think it is applicable to this, right? Because of this intersection. So we're asking for chances that both E and F happen, right? But anyway, okay. Okay, so and then pairwise independent, it's still what you would think of as independent, but in the case before, we said that our spaces, our sets were completely disjoint. There was no overlap, and so pairwise independent is just that same concept but applied to all of these. So if you flip a coin n times, if you flip a coin 100 times, each one of those flips is independent with every other one of the flips, and so you would say that those are pairwise independent. And so this formula would apply to any 2 trials where I is not equal to j. So if I is equal to j and it's a 50-50 chance of getting heads, then if you allowed that to happen, then this formula would not necessarily apply, because over here you would have it happens 1 out of 2 times and 1 out of 2 times, and so you get the chance that the 25th flip was heads is equal to 1/4 instead of 1/2, right? So that's why I and j can't equal each other, right? Like, these have to be distinct trials, and then again, pairwise independent just means it's independent, but it applies to any pair of samples from within your sample space. And then the events are mutually independent, basically if that's true for every pair, right? And so you can measure that directly. You can extract this quality if you're given that this is true. Okay. And then Bernoulli trials, it's another name for a coin flip, or the terminology that they use formally is that it's a success or failure, but it'd be Bernoulli. It just means if it's one or the other, right? If there's only 2 possible outcomes. So heads or tails, true or false, win or lose, 1 or 0. Those would all be considered Bernoulli. Win or lose, like in games that don't have a draw, right? so there is no third outcome. You're only given 1 of 2 possible outcomes, right? Okay. And then these are always mutually independent. So here we have the likelihood of Bernoulli trials, where you want to know, so if you flipped a coin 100 times and you want to know what are the chances that it came up heads exactly 40 times, I think is the book used in the example used in the book, then this is your formula. So you do n choose k times 1/2 to the 40 times 1/2 to the 60, 100 minus 40. Right? And so that would give you the overall likelihood of getting that. And so this combinations is just the number of times that you could get 40 out of 100 flips. So you could get it if it's the first 40 coin flips. It's extremely unlikely that would happen, although any one string of 100 possible results is individually unlikely. Right? You could get it if the second coin flip through the 41st coin flip were all heads, and then every other one was tails, or the third coin flip through the 42nd were all heads, and so forth. And then if the first 20 and the last 20, and so forth. So this is just the number of those scenarios, right, that satisfy the condition, and then times this, right? And so this is just the binomial distribution. So this formula is derived essentially from this. You have a binomial. You have raised to a power, so you would get a polynomial. Right? So if this was x plus 1, then this would be 1 over here. This would be x to the k power, and this would be the coefficient for it. So you've probably seen this formula before, but its name is the binomial distribution, and it is applicable to Bernoulli trials. Okay, so will you ever use this? Maybe, if you go into research or whatever. You won't be required to memorize it, but kind of what I want you to do as you go through this class is not, at least for me, right? Like I will try to prepare you for all of the homeworks and exams so that it doesn't feel like like I'm trying to get you or trying to find weakness in your method of study or anything. I really just want to expose you and hopefully do it, through repetition as well, so that you become familiar with it, with a lot of these concepts as you go, so that whenever years down the line, or maybe just months down the line, it doesn't, you never know. Whenever you look back and you're trying to find the answer to some question, or find what formula applies, or what to use in a given situation, that you have this this familiarity, this intuition of where you should look for it, or where you've seen it before. And so that's kind of the motivation behind going with the speed that I'm trying to maintain here. And so I wouldn't expect you to memorize this for 20 years at a stretch, especially if it doesn't come up. But I do hope that you become comfortable and familiar with the process of learning things quickly, and maybe not to absolute certainty and irrevocable memory or whatever. I really I want you to become comfortable with mixing and matching both computer science knowledge with domain knowledge, because that is kind of what you're going to do whenever you find employment. You will go to some employer and they'll have some domain that they work in, and you will have to know both how to program and how to design your applications, and what patterns are really good to use, where you'll have to adapt whenever conditions change and you have to make modifications. You'll have to kind of remember where in the code everything is kept and so forth, and you add certain business functions and and so you have to accommodate those as well. And so you'll always be kind of reworking and patching or whatever, but hopefully you'll have some solid design from the beginning. But in addition to that, you're going to have to know what it is that your customer is doing, and you'll have to be familiar with that business, that business knowledge, so that you can implement it correctly, so that if you are not thrilled by the prospect of dealing directly with customers or whoever else, that you can kind of anticipate their needs, so that to save you the conversation, you can kind of at least present a reasonable default that'll get them going, and so it'll make some of these conversations easier. And so it's unlikely that any of you will find degenerate gamblers as employers, and so that you'll need to implement every one of these formulae or whatever. But these things pop up in weird places, and so it's always nice to just have this vague recollection of where you can go to find that thing that you think explains whatever phenomena it is that you're seeing, right? And so just remember that you've kind of seen this someplace before, and maybe you'll come back to it. Okay, so one last definition. We'll pick up with Bayes' theorem next time. And then it's just a random variable, right? And so it maps some sample space to some real number, and that's it. You already know what a random variable is. I'm not exactly sure why I included that, but anyway. So again, I don't expect you to memorize everything, and especially given the format of the way that this class is being taught this semester, you will have access to all of your notes, and I'm not particularly concerned with limiting your availability of resources whenever I test you on particular areas. I do hope to prepare you in advance for those exams, and then I am fine with you using notes and books and stuff as you attempt to answer it, as you would once you get out in the professional world. Maybe not for business meetings and stuff like that, but whenever you're working, whenever you're doing the core of your work, you will typically have those resources available to you. But more than that, and as I do these tutorials and bonus videos or anything else in that nature, I want to expose you to the idea that the job entails more than just programming. That is part of it, but you're programming to solve a problem either for yourself or for someone else. And so again, there are these patterns that you'll kind of have to learn along the way, just as tricks of the trade. So you'll develop your trade knowledge, and then in whatever business you're working in, whatever industry you're working in, there will be domain knowledge that accompanies that. And so your job of learning, even once you become this sort of master of software development, it's still not complete. You're still having to add all of this additional knowledge. And I would hope that rather than being disgusted or intimidated by that concept, that you're kind of thrilled at the prospect that the journey's never quite completed, that there is always a little bit more to learn along the way, and the adventure never really stops. So okay, I hope y'all have a great weekend, and if all goes well, that next Tuesday's recording will be uploaded in a slightly earlier in the day, and I will have homework 2 ready for you. Okay, have a great weekend.